So we have two levels of the theory, and now we're going to talk about a third level. We have a theory of curvature where we have Riemann curvatures, these things, based on connections, right, with the three indices. Now we're going to find a third level. Over here we had tidal acceleration. Over here we had gravitational acceleration. And now we're going to look for the third level. And once we do that, we'll also be able to set up and solve Einstein equations. We know that if you have a coordinate system, if you have a distance in a coordinate system of r theta phi, you would write it like this. Right? The connection coefficients that we found, the r thetas, were 1 over r. How do you find these from this? The answer is you take, if you call this function over here, which is just 1, call that grr. Call this function g theta theta. It's the little function in front of the theta theta. This one is r squared sine squared. If you take the derivative of this with respect to r, what do you get? 2r. Okay, 2r. And divide it by itself. So you have g theta theta prime over another g theta theta derivative with respect to r over g theta theta. Okay, what is g theta theta derivative with respect to r?
2r.
2r over r squared, which is 2 over r. If you put a 2 in here, 1 over r. So this is the formula to get the connection from the metric. Okay. Now let me ask you a question. Does space-time have a metric? We know that space-time has Riemann curvature. We know that it has a connection. Does space-time have a metric? Now we know from special relativity, of course, that it does, but it's not a curved metric. Could we find some way to tell us that space-time has a metric, or at least this time warping that we've been talking about, right? Is that a metric quantity? But we don't know special relativity. So I'll show you a reason why one might suspect that it is. All right? We know that a connection is basically the derivative of a metric coefficient. Okay? We know that we have a connection in our theory. Okay? We know that we're going to have some kind of a connection like this. The question is there some quantity that this is it's actually a gradient or a derivative of? Is there something here? So the answer is we know that this projects down in the flat space-time theory to what? To the world line curvature, which is the acceleration. And this, in gravity theory, does it have something that it is a derivative of, gradient of?
Potential.
Potential. Grad phi or phi prime, just for spherical symmetry, it's just phi prime. So in gravity theory, there is something that the acceleration is the gradient or derivative of. And in differential geometry, we know that sometimes the connection can be built out of a metric, in which case it'll be the derivative of it. So we can therefore maybe have reason to suspect that it would have a metric. And in fact, g is the symbol for the metric thing. We'll expect that grad g is grad phi, or g prime is phi prime, which means that if we integrate it out, we'll get g is equal to some constant a plus b phi. Okay?